So let's see if we can do another example of using Stoke's theorem to find the integral over surface S of the curl of f dot d area, where thankfully they give me the vector field f. You guys see that? If they had just given me the curl of f, I would have a bear of a time trying to find the vector field f. Thankfully they gave it to me, right? And it's xz, comma yz, comma xy. And they tell me S is the part of this x squared plus y squared plus z squared is 4, is a sphere, radius 2. Inside x squared plus y squared is 1, which is a cylinder above the xy plane. So why is it important they said above the xy plane? Yeah, there'd be 2 halves, right? And then I'd have to calculate 2 of these and add them together or something. That would be weird. Okay? They also should have told me that S is oriented in some direction. So which way is S going to be oriented?
Upward.
Probably upward. Okay, so I've got a sphere, cylinder, cylinder. I really only care about the top half, so I'm going to erase the bottom half of the sphere. Here's your surface S, right? That's this kind of cap thing. Oriented upward. And what does Stoke's theorem say? Find Stoke's.
The integral of the circulation.
Okay, the circulation integral, f dotted with dr,
equals what it's asking.
is very conveniently, right, the thing they asked me for. Okay, integral over S of the curl of f dotted with d area. Okay, so I don't have to calculate anything about this curl business, right? Because they told me to use Stoke's, and the other half of Stoke's is a line integral, right? So when I'm trying to calculate a line integral, what do I need? I need a parameterization. So where's that curve C? Just see it there.
It's a slight feature.
S is this little hemisphere thing, right?
That's a circle.
That's, okay, let me blow S up. S is something like this. Okay, see that? It's a little cap. Now, where's your curve C? Yeah, it's perfect, Jason. It's got to be the bottom circle, right? It can't be anything else. If this thing's pointed up, which way am I going around the bottom circle? Yeah, it's got to be right-hand rule-y, right?
Yep.
So here's your curve C. It's this circle. That's not in the xy plane, right? Okay, but it's parallel to it. So hopefully this is chill. So I want to know about C. So to know about C, I need an R of t, right? Or maybe, what would be a better variable choice? Probably theta, right? I'm going around a circle. So what do you know about R of theta?
Z can be anything.
Z should be specified, right? It should be constant.
Yeah.
Say that again?
Cosine, sine, and 1.
Yeah, it should be cosine theta, sine theta, right? The radius of the circle you're going around is 1, right?
Yeah.
Because it's part of the cylinder, that's a radius 1.
Okay.
And then the Z value, I like your thought 1. Unfortunately, that's not quite right. Where do I get the z value from? Perfect. Substitution, right? That's the, this business happens, right? Where this sphere hits that cylinder.
So square root of 3.
Perfect. Square root of 3. Cool.
Yep.
That's take the x squared plus y squared is 1, jam it in there. Right? You'll find out that the x squareds and the y squareds cancel. Right? Because you're replacing them with 1. And then the z's are plus or minus the square root of 3, and we're above the x-axis, the xy plane, so we're looking at the square root of 3 there. Cool. There's your curve C. So what do I need to calculate the integral of the circulation around a curve C of f dot dr? This is just a line integral calculation. Perfect. So I need to do the integral of f of r of theta dotted with r prime of theta d theta. And where are your bounds? 0 to 2 pi, because you want to go all the way around the circle, right? Nice. Good. Okay. Okay, calculate some bits and pieces. Bits and bobs. What are your bits and bobs?
Cosine
root 3, sine root 3, and
Okay. Cosine theta times square root of 3. Oh god. Comma sine theta times the square root of 3, comma cosine theta sine theta. Oh god. It's gonna be horrible. And r prime is, oops, and I need a d theta. D theta.
I don't think it's very wise.
Negative sine theta.
Well, this is no longer chill.
Negative sine theta, comma cosine theta, comma 0. Oh, good.
No, that's theta.
That's
0
zero.
theta.
Oh, what the hell?
Autopilot.
Okay, don't cross your zeros in any direction.
Theta or phi? Yeah.
Okay, so what's the dot product? What do I get? I got the integral from 0 to 2 pi of negative cosine theta sine theta root 3. Good.
Same thing as nothing.
Plus. Did I screw something up?
Yeah, I was just saying the same thing.
Plus the
not
same
negative.
thing, so not negative.
Oh, plus the same thing but not negative.
That's nice.
Good.
That cancels.
Cosine theta sine theta square root of 3.
And then another one's here, so.
Excellent. Those cancel.
Plus 0.
Plus 0. D theta. You bunch of whiners. Equals 0.
Okay, that's kind of chill.
That's kind of chill, right? Okay, so what did you find?
That there's
Doesn't do anything.
no net flow through that. Yeah.
Yeah, so the vector field curl F has no net flow through the surface S. Or, right, according to Stokes, the circulation of the vector field F around this little circle is nothing. It's nothing. So, no tendency to hurt or harm, right?
Yeah.
Cool. Question 6.
You mean help or harm? 'Cause
Yeah,
you
what
just
does
said
that-
double negatives. Hurt or harm.
Hurt or harm. Yeah, help or harm. Whatever. All right, cool. Other things?